Okay, physical and chemical change. All right, physical change. This is the one where the substance itself doesn't actually change. So physical change can be change in shape, change in color, but generally a change that can revert back. Like, in other words, if you have a stove, a plate on a stove that gets red hot, the color changes to that red because it's nice and hot, but when it cools down, it will go back to black. So color changes that are temporary are physical changes. Change in shape, all right? You can take a piece of wood, cut it into different little pieces, or take some clay and mold it into different shapes. That's a physical change, just a shape change, but the substance is still the same, okay? Another big physical change, and one that kind of forms the basis of what we're looking at in science here, is the phase changes. So if you have any substance can really exist in any phase. So you can have substances that can be in solid phase, heat them up a little bit and then go to liquid phase, heat them up a little bit more and they go to gaseous phase. Those phase changes are only physical changes because the substance stays the same. If you think about water in ice form, water in liquid water form, or water as steam, all the particles are still H2O particles. So they haven't changed their properties. They haven't changed what the actual substance is. It's just in a different phase. Okay, so that's a physical change. Now, a physical change does involve a little bit of energy shifting, but very small amounts of energy in comparison to chemical change. So chemical change generally involves quite a lot of energy change. Physical change, really small amounts of physical change. Okay, so in other words, if you think about your water particles again, so water can either be water, liquid, gas, or solid phase, but either way, it's just H2O particles, okay? The H2O particles don't change. That formula doesn't change. But if you had to change that in a chemical change, in other words, change that to hydrogen and oxygen, now it's chemical change, the substance is changing. And to do that, you don't just heat it up, you actually have to put electricity through that to break up your water particles. So chemical change generally involves a lot of energy, and physical change only small amounts of energy. Okay. All right. Physical changes are easy to reverse. Okay, this depends on what kind of physical change it is. If you take ingredients for a cake, okay, and you go mix all your ingredients together, it is just a mixture, and you haven't formed new bonds with new properties, but it's really hard to unmix egg once you've mixed it into batter. So not all physical change is reversible, but mostly it is reversible. Okay. Chemical changes, on the other hand, are more difficult to reverse. Okay, so the cake batter example would be once you've baked it, then you're going to start forming new bonds with new properties. So those are more difficult to reverse, but generally speaking, physical changes are reversible with relatively low amounts of energy most of the time. Okay. All right. No new substances are formed. Number 2 is very, very important. And it's actually the crux of the whole thing. The physical change, you still have the same compounds with the same formula, the same properties, and those properties don't change. But as soon as you start forming compounds with new properties, then it's a chemical change. Okay. And in small amounts of energy involved. So if we have a look at the chemical change, they're hard to reverse, much harder to reverse. Some of them are reversible with large amounts of energy. So if you take your water example again, you can reverse that. You can split water up into hydrogen and oxygen, and then you can react hydrogen and oxygen with each other and form water again. So some of the chemical changes are reversible, but they require much more energy. Okay. Other kinds of chemical reactions are not reversible. So if you burn your toast, you are never going to have that toast unburnt ever again. Okay, so some of them aren't reversible. All right, in the chemical change, new substances form with new properties. So once you take your cake batter and you put it into the oven, after a while you start smelling something, okay, and it starts to smell nice. You can actually smell that it's nearly ready. Now, those compounds that you're smelling are actually new compounds that have formed and are being released into the air, and that's what's prickling your nose there. So any smell changes, permanent color changes, those are indications that you may have a chemical change taking place. Okay, especially if something has generated a smell that wasn't there before. Anything that you smell is a compound, right? So if the smell wasn't there before, and now all of a sudden the smell is there, it means that compound has formed. All right, so that's chemical change, right? So new substances form with new properties. And then large energy changes are involved in that. Amali, did you want to ask something? I saw you unmuted. No? Okay. All right, guys, so that's the difference between physical change and chemical change. All right, so the examples that we've got here, we've got for the water and the ice one, and then on the other side of the chemical change, we've got rusting. Now, rusting is a reaction with metals and oxygen. That rust that forms is an oxide, so an iron oxide, for example, that you see over there. That is a new compound with new properties. How do we know it has new properties? Well, one of the properties of iron is that it is magnetic. Okay, so guys, please remember, not all metals are magnetic. Only iron, nickel, cobalt, those are your magnetic metals. Okay, but iron is one of the magnetic metals. So iron itself has got magnetic properties. But the iron oxide that forms is not magnetic. Okay, so that magnetism property of iron has changed when the iron oxide forms. You also see a color change, a permanent color change. So it goes from that nice silvery color to a bronzy color. So that rust color of rust, that reddish brown color. So you have a color change as well. And very, very, very difficult to revert back. Okay, possible using a lot of electricity, but difficult. Okay, so not easily to revert back like you would make ice and then melt it again. Very easy to switch that physical change back, but a chemical change does require a little bit more energy to do that. Okay, so that's the difference between physical change and chemical change. Here's one example of evaporation. So you've got your water particles. Now, with this, there's two types of forces that you'll find in water or amongst water particles. You need to know which ones are involved in the physical change. If you have a look at a water particle, so let's say these little ones over here on the screen, there is a bond between the hydrogen atoms and the oxygen atom, okay? Those bonds are very strong, and to break those bonds requires a lot of energy, the electricity energy, okay? That is a bond that you would break in a chemical change. In a physical change, there's forces as well. So there's forces that act between these particles. Now, in this liquid phase, the forces are quite weak already, but in the gaseous phase, the forces are even weaker. So the forces between the particles, not within the particle itself, but between two separate particles, are forces. Now, if you weaken those forces, you get the phase change. You can weaken those forces quite easily with a little bit of heat, okay? But once the forces will weaken first, the bond will only break if you add much more energy. So physical change will happen first. Chemical change will require much more energy. So in this one over here, going from liquid to gaseous phase, you start off with your particles with those forces a little bit stronger. The particles are able to move around each other, but they are still holding on to each other. They're still in contact with each other, right? They're like rolling over each other. Now, when you add a little bit of energy, what you're actually doing to the particles is you're starting to move those particles a little bit faster, okay? A temperature change is very closely related to the kinetic energy of the particles themselves. So if you add temperature to particles, you're increasing kinetic energy in the particles. The particles start moving faster and faster and faster and faster. That movement causes those forces between the particles to weaken. And eventually the forces become so weak that the particle can escape altogether. And now because the particle has so much kinetic energy, it moves around freely in different directions. And that's your gaseous phase. So it's weakening the forces between the molecules. That's what the phase change really is. So the forces between water particles are quite weak, but when you get to a gaseous phase, the forces are very, very weak, not really there. In an ideal gas, we actually say that there are no forces between the gas particles. So you'll find your smaller gas particles like hydrogen, helium, they kind of don't really have forces between them. The bigger ones will have small forces between them, but yeah, very, very weak to no forces between gas particles. Okay, there's a question in the chat quickly. Masindi, yes, you're 100% right, guys. So the question is how it's supposed to be a chemical change. Is the outside that's affected? Yes, the chemical change actually happens on the outside. That's right. If you burn it all the way through, the chemical change can get to the middle as well. Depends on how badly you burnt your toast. But yes, it is only the outside particles that generally get affected. It's basically a bit of almost a combustion reaction, almost. You heat bread up like that, it is an organic compound, it does react with oxygen, and that's actually what that black char is. Not good for you, by the way. It's not good to eat that black char. Okay, but yes, Masindi, you're right. It's the outside first that gets affected. Good. Okay, so the parts that don't look like bread anymore. Okay, so the movement there, guys, then that goes with the forces. Obviously, when the water particles are rolling over each other, when they're still touching each other, they just roll over each other. But when the forces weaken so much, then they move in different directions. Keep in mind, though, gas particles move in straight lines until they collide with other particles or sides of a container. Okay, so they don't like change direction halfway through their movement. They move in different directions, but straight line different directions. Okay. All right, here's an example of chemical change. So this one is the decomposition of hydrogen peroxide. Now, before we talk about the chemical change, I want you guys just to notice the properties, okay? Because remember we said that chemical change involves change and new substances forming with new properties, okay? And that's the very important part about this. Now, our substances bond together, our elements bond together in very specific ratios. If those ratios change at all in the slightest, then the properties will change. Then it is a new compound, a new substance with new properties. So if you have a look at the peroxide, H2O2, our ratio of hydrogen to oxygen here is a 2:2 ratio, okay? 2 hydrogens for 2 oxygens. Water, 2 hydrogens for 1 oxygen. So the ratio is different, okay? Very slightly different. You're talking about 1 oxygen difference over here. So these two compounds look very, very similar, but that small difference in the ratio changes everything. This peroxide, H2O2, is the peroxide you'll put in your hair to bleach your hair. The one that smells so bad. Okay, really pungent smell. You cannot drink that. that will harm you badly. You will end up in hospital. Water, on the other hand, you have to drink. Necessary, okay, to stay alive. So that small difference in the compound changes the properties dramatically. The ratio of the elements in that compound changes everything. Okay, so the H2O2, the peroxide, decomposes to form hydrogen and oxygen gas. So again, here, look here, there's the look at where the bonds are. If you look here in the hydrogen peroxide, you have a bond between your carbons. You have a bond between carbon and hydrogen, and another, sorry, why am I saying carbon? Oxygen and hydrogen, and another bond between oxygen and hydrogen. Now, those bonds will break. There's two separate molecules, and in each molecule you have these bonds. Those bonds will break. Then the atoms reshuffle, okay? And now you have an oxygen only bonded to two hydrogens, and then you have a separate molecule with an oxygen-oxygen bond, okay? So in other words, in this chemical change, some bonds have been broken and new bonds have been formed. Those bonds require a lot of energy to break, and they release a lot of energy when they form again. So this energy change in chemical change is much greater than the energy change for physical change, because now it's not the forces that are being overcome anymore, it's the bonds that are breaking and new bonds that are forming. So you'll always put energy in to break bonds, and energy will always be released when the new bonds form. Okay, the difference in that, if you require more energy to break the bonds, then it's an endothermic reaction, okay, and the reaction will generally cool down the environment, or it will always require some source of heat to keep going. If more energy is released when the bonds form, then we call that an exothermic reaction, because overall you will have more energy being released into the environment, and the environment will generally heat up. So the difference in the amount of energy absorbed and the amount of energy released, that difference will determine whether your reaction is endothermic or exothermic. But all chemical reactions do both, absorb energy and release energy. Okay, it just depends which one happens more. Okay, now in chemical change, a really important factor here is that your atoms cannot change from one type of atom into another type of atom. The atoms, every single atom that goes into the chemical reaction comes out of the chemical reaction, okay? And that's our conservation of matter. So you can't create matter out of nothing, and you can't destroy any matter, okay? The atoms will just break loose, reshuffle, and form products. Now, because of this, because every atom that goes in has to come out again, the total mass of the system will stay the same. Okay, so the total mass before the reaction and after the reaction will be constant, because you're dealing with the same atoms. You're just shuffling them around. Ebenezer, your question in the chat, yes. Guys, the question is, if it's a nuclear change, can the atoms change into different ones? Yes, nuclear change involves splitting of the atom cores, and when they do that, they do become other substances, yes, but that is nuclear change, not chemical change. So keep that in mind as well. Nuclear change is something completely separate to chemical change. In chemical change, no atoms will be created or destroyed. And even in nuclear change, even if it is a splitting of a core, the protons, electrons, and neutrons involved don't disappear. They don't turn into nothing. You can still account for them. Okay. So you will still conserve your matter in a nuclear change, but yes, the type of atom can change then. Right. You guys don't have nuclear change, is not part of your syllabus. So if anybody's freaking out and thinking that they missed something along the way, nuclear change is not in your syllabus. But yes, it's a good one for interest. Awesome. Okay. Right, what was I saying? Oh, okay, so we're talking about our conservation of matter in chemical change. All right, so if we have a look here at our total reaction, in this word equation over here, we can talk about our substances in words. Hydrogen and nitrogen is going to give us ammonia. We can put that into chemical symbols as well in our formula. Hydrogen is H2 gas, nitrogen is N2 gas. These are two diatomic gases. Now, I just want to clear something up for you guys. A diatomic gas means that if the substance is on its own, all right, in its natural state, it exists as two atoms bonded together. So if we have a cylinder of oxygen gas, that oxygen gas will exist as two oxygen atoms together. If we have a cylinder of nitrogen gas, that nitrogen gas will exist as 2 nitrogen atoms together. But when the molecules, the nitrogen molecules, the oxygen molecules, the hydrogen molecules, when they're involved in chemical change and they bond to any other element, they're not diatomic. They're only diatomic in their natural state when you're talking about the substance itself. For example, hydrogen gas is H2 gas. Okay, that's a diatomic gas particle. In water, H2O, it's not diatomic. That H2 does not mean a diatomic gas. These hydrogens aren't bonded to each other anyway. Each one is bonded to an oxygen. So just because there's 2 hydrogens doesn't have anything to do with the fact that they're diatomic. It's only when they're in their natural state, just as a substance itself. Okay, I just wanted to clear that up because I find that is something that gets confused quite often. All right, so if any of you guys were confused about that, or even if you're still confused about that, just let me know and I'll re-explain. So we have 2 diatomic gas particles here, hydrogen gas and nitrogen gas, and then those atoms will reshuffle and form ammonia. Now, ammonia here, you've got a nitrogen particle or nitrogen atom bonded to 3 hydrogen atoms. Okay. Now, we need to balance this equation. We can't just have 2 hydrogens, 2 nitrogens giving us 1 nitrogen and 3 hydrogens. That doesn't make sense, okay? Because then we've lost something along the way. So we need to balance this. We need to make sure that each hydrogen that goes in comes out and each nitrogen that goes in comes out. You cannot change this little subscript, okay? The 2 here for the hydrogen, a 2 there for the nitrogen, and a 3 there for the hydrogen. You cannot change those subscripts because, like you saw with the peroxide, if you change the subscript, you change the substance. Then it's a different substance. The only thing you can do is add a coefficient to the front of this equation when you balance it. That coefficient on the front will tell you that you've got 2 of those molecules or 3 of those molecules. Okay, so you're adding in another molecule of the same substance. You're not changing the substance. So if you start here, we have a look here. We've got 3 hydrogens and 2 hydrogens. To get those 2 hydrogens to be equal, we look for a lowest common multiple, and that would be 6. So 3 times 2 is equal to 6. So we put a 3 in the front, and 2 times 3 is equal to 6. So we put a 2 in the front. Now our hydrogens are balanced. We have 6 hydrogens on either side. And when we check our nitrogens, this 2 in the front of the ammonia, that will count for the nitrogen and for the hydrogen. So 2 times 1 is 1 nitrogen in that compound. 2 times 1 will give us 2 nitrogens in total. And here on the left, we also have 2 nitrogens. So the nitrogens also balance. So that is a balanced chemical equation. Guys, please just notice the terminology here. The whole thing is an equation. So formula plus formula with the arrow gives you another formula. The whole thing is an equation. Each substance has its own formula. So the formula for hydrogen gas is H2. The formula for nitrogen gas is N2. The formula for ammonia is NH3. Okay, so you have 3 formula and 1 equation. All right, just notice the difference there. Okay, so if you count your atoms now, we said we've got 6 hydrogens have gone in, 2 nitrogens have gone in, and we see that the same thing has come out on the other side. So when we add the mass of our reaction, we should have the same mass in the beginning and the same mass at the end. So we can look at our molar mass. We can say for our 3 hydrogens, it's 3 times now. They've got here 1 plus 1. That 1 plus 1 is for each hydrogen, okay, in the hydrogen molecule. And then there's 1 nitrogen molecule. So 1 times, we've got 14 plus 14. Those 14s are for the molar mass of each nitrogen atom. If we add all of that together, we get a molar mass of 34. Now, we can do the same thing on the side. We've got 2 ammonia molecules. So 2 times. Now, in the ammonia molecule, there's 1 nitrogen. So that's the 14. And 3 hydrogens. So that's the 1 plus 1 plus 1. If we add all of that together, we also get 34. So the mass has stayed the same on either side of the equation. The energy that you would need to break on this side, you would have to break the bonds between 3 hydrogen molecules and 1 nitrogen molecule. And then the energy that's released here would be the energy for 2 molecules, each molecule having 3 hydrogen-nitrogen bonds. Okay, so you'd have to break all 3 of those, all 3 of those bonds form for 2 molecules. So that for each one of those bonds that form, energy will be released. So there's a lot of energy change here. Okay, I'm just going to read the chat. There's a couple of questions in the chat again quickly. Matthew, are you on the nuclear change again? I always find this, guys. One person starts talking about nuclear change, it suddenly becomes far more interesting than chemical change. So the questions just start rolling in, but that's fine. It is interesting. Matthew, so your question there. So is the atom split into 2, or is it rejoined back into 1? Both is nuclear change. Okay, so it's fission and fusion. I don't know, you probably heard those words somewhere before. Fission, the atom splits into different atoms, and fusion, 2 atoms form a new one. But both of those would be nuclear change because you're involving changing of the nucleus. Okay, again, separate from chemical change, hey? Separate from chemical change. And yes, Ebenezer, that is exactly how atomic bombs are made. That's what nuclear change is. The energy involved in nuclear change, guys, is a whole nother level of energy. I mean, we talk about physical change that involves a little bit of energy, chemical change that involves a little bit more energy. Nuclear change is like a whole new realm on its own. That is a lot of energy that you're talking about there. Okay, I'm going to come back to chemical change now. Miss Cindy, your question there, would they specify whether ammonia or ammonium is formed, or would we just have to know miraculously? No. Ammonia is a substance on its own. So ammonia, NH3, this one that we've got here, this is Handy Andy. So if you've ever smelled that really pungent smell in Handy Andy, that's what ammonia is. Okay, it's a cleaning agent, it's a base. Ammonium is actually one of your complex ions. So ammonium would be NH4+, and they would tell you that this is forming, but it wouldn't form just that on its own. So a complex ion is still a relatively unstable substance. It's not like an ammonia molecule, right? So it's an ion. Now, if that ion forms, it's generally bonded to something else. So it might form magnesium, what am I saying? Ammonium nitrate or ammonium hydroxide. So or ammonium chloride. It'll form ammonium something, okay, as a substance, because it's, as an ion, it's just part of the substance, okay? It needs to go with something else to be stable, to be a substance on its own. I hope that makes sense. So the only place ammonium can really exist by itself is if the substance it was bonded to has dissolved in water, and you'll have a little ammonium ion floating in an aqueous solution. That's the only place you really find the ammonium by itself, but it's not a substance on its own. Okay. Cool. Okay, Ebenezer, last question on nuclear change, because I think we're going to start getting confused here. But yeah, that is pretty interesting though. So can you turn, if you can turn atoms into different atoms, can you just make gold? Yes, technically. The only problem is that the whole process is kind of random and dangerous, because you've got it's like radioactivity that comes off of those changes. So you could theoretically, but it's a random process. So when atoms split, they split into whatever. You can't really control it. But technically, yes, maybe down the line, that would be really expensive gold then. Definitely gold price would shoot up like crazy if that was how we were making gold. But technically, yeah. Okay, I mean, you take what, three atoms away from lead and you have gold. So in theory, yes, maybe you must go into that direction, Ebenezer, and see. Maybe that's a line of work you can pursue one day. Matthew, so Matthew, your question here, you're actually touching on chemical change. So you're saying, couldn't you technically also make water? Yes, we can make water. If you have a tank of hydrogen gas and a tank of oxygen gas and you react the two together, it gives off a lot of energy. But yes, the product that forms is water. So you can make water. The only thing is, that's chemical change, hey Matthew. So making water is chemical change, not nuclear change. That's chemical change. That's reacting. That's taking two substances, reacting them together, and then water is the product of that. The only thing is, it's not viable to make water that way because the amount of hydrogen and oxygen gas you'll need to do that is immense. We actually use the process the other way around. We actually use water to give us the two gases because we use the gases for other reactions and other processes. So we generally use that process the other way around. It's just not viable economically to make water that way. But yes, in theory, yes, we can make water. And it's dangerous. Yes, it is. It does give off quite an explosion. Hydrogen gas and oxygen gas reacting together is very exothermic, gives off a very loud, big explosion. It releases a lot of energy. So the water that's formed as well, because of all that energy that's released, the water that's formed is in a vapor phase. So also to try and do that under a condition where you can actually collect the water is quite hard. But in theory, yes, we can. Okay, cool. All right, guys, anybody else have any other questions on this? It's a really interesting topic. It's a very cool topic. Okay. Chemical change I'm talking about. All right, should we have a look at the questions that you guys have got? Stoichiometry is not a favorite in grade 10, guys. So if you're busy doing stoichiometry at the moment and you're just hating this topic, it won't be a horrible topic forever, okay? You will get to a point where stoichiometry will start making more sense and you'll start being able to do it without thinking so hard, okay? It'll come a little bit easier. Now, we're going to practice a little bit of stoichiometry because this is a really good thing to practice. Really one of the topics that does need a lot of practice. And the more you practice it, the quicker you'll start seeing what it is that you need to do. Okay. All right, our first question here says a group of learners prepare a 0.25 molar solution of sodium carbonate. So this 0.25 mole per cubic decimeter, okay, mole per cubic decimeter. That is a concentration. So they've given you the concentration of sodium carbonate. Okay, sodium carbonate is, they've actually given you the formula here, but it is Na2CO3. By dissolving a 14.2 gram sample, so that's a mass that they've given us there, of hydrated sodium carbonate in 200 moles of water. Okay, now let's just talk about this hydrated sodium carbonate for a second here. You'll see that in between these two, there is a little dot. That dot is not a multiplication sign. That dot means that there's a light bond. Now, sodium carbonate is one of your ionic substances. So I don't know if everybody has done different bonding yet, but it is an ionic substance and therefore a type of salt. Now, it forms a lattice. The ions in sodium carbonate forms a lattice. So the sodium, positive sodium ion, the negative carbonate ion, they bond together and they form a lattice, okay, a crystal lattice. Now, in that crystal lattice, it can happen that water molecules become trapped. So when the water molecules become trapped, we call it hydrated, okay, it's a hydrated salt. So those trapped water molecules, you can have a certain number of water molecules per formula unit of sodium carbonate. Okay, a formula unit is the correct term for a molecule if you're talking about an ionic substance. We don't really talk about molecules for ionic substances. So in other words, for every one NaCO3, you have a certain number of water molecules attracted to that. Okay, so there is a ratio between the sodium carbonates and the waters. There's a ratio between those two. Okay, a certain number of waters can be attracted to each sodium carbonate particle. Okay, so that's what the hydrated sodium carbonate is. Okay, it's the sodium carbonate with trapped water. Now, the 200 moles of water, so we've got a volume here of water, 200 moles of water. The cubic centimeter, okay, cubic centimeter is equivalent to a milliliter. The cubic decimeter is equivalent to a liter. Okay, we always need to be working in liters. So if you need to convert from a cubic centimeter to a cubic decimeter, you're going to divide by 1,000 to do that. So that's why I automatically read that as a milliliter, okay? Because in my mind, I think about that as a milliliter, and it's easy to convert milliliters to liters. You know how to do that already. So the cubic centimeter to a cubic decimeter is the same as converting a milliliter to a liter. You divide by 1,000. So our first question here says, explain the meaning of the term hydrated. Okay, so that is what we were talking about now. The hydrated means that our salt particle is surrounded by water molecules. Okay, there is water molecules around our ionic salt. Write down a balanced chemical equation to show how sodium carbonate dissociates in water. Okay, dissociates, there's another word. Dissociation is the process where salts will separate into the ions in water. Okay, some salts are not soluble. So some salts don't dissolve in water, and then they don't dissociate in water. But the salts that do dissolve, that are soluble, those salts will separate into their ions in water. Okay, so you're looking at the separation of the salt. So we're looking at Na2CO3. It's going to dissociate in the water. What I'm going to do here is put the water on top of the arrow to show that that is, or that's in a bracket, to show that that is my solvent. Okay. The salt is generally in a solid form. The water is in a liquid form. So I've got my liquid there. Now it's going to separate into its ions. So I'm going to get sodium plus ions, and I'm going to get carbonate 2 minus ions. Okay, these ions, because they're in an aqueous solution, they get the phase aqua in a bracket. Okay, both of them. Anything that's an ion will be in aqueous phase. If you see anything that has a charge on it, it is an aqueous phase. Now, let's talk about how I know what the charges are on the sodium and the carbonate. Okay, the one you're not going to like is the carbonate. You have to learn that. It's one of your complex ions. You have to know your complex ions. If you don't know your complex ions, you will always struggle with this section. All right. So how do I know what the sodium is? On your periodic table, I'm just going to switch to a periodic table here. On your periodic table, just make sure I got the right one. Yeah. Okay. So on your periodic table, you've got at the top here, +1 for hydrogen, +2 for beryllium, +3, plus or minus 4, -3, -2, -1. That pattern you need to remember. Okay, those are the charges that these elements will get when they are in their ion form. Now, sodium is in the group that's +1, and that's why I know that sodium is a +1 ion. Okay, so you can write that down. If you don't have it, it goes 1, 2, 3, 4, and then backwards 3, 2, 1. The noble gases don't have a charge because they don't form ions ever. Okay, they don't ever form ions. They don't react with anything. All right, so I'm going to go back to the other screen. Okay, so that's the sodium +1 I get from our periodic table, and the carbonate I need to learn, CO3 2 minus. Okay, part of the learning work. Guys, I can guarantee you that as soon as you know your complex ions off by heart, a lot of these chapters will suddenly become a lot easier. Okay, that feeling that you have where I don't know why you do it like that, or I don't know how you know that it's like that, that feeling will start to go away. All right, so as soon as you know your complex ions, a lot of the stuff will make much more sense. All right, so that is our dissociation reaction there. Learners then take 10 milliliters of the prepared solution and allow it to react completely with 5 milliliters of dilute hydrochloric acid, according to the following balanced chemical equation. So we've got our sodium carbonate plus our hydrochloric acid gives us sodium chloride plus water plus carbonate. Carbon dioxide. Now, it's balanced, so we've got 2 hydrochloric acids and 2 salts that form on the other side. Define the term 1 mole of a substance. It is the amount of substance that has the same number of particles as there is in 12 grams of carbon 12. Okay, that is just a definition that you have to remember. What type of chemical reaction is represented by the chemical equation above? Now, the sodium carbonate is a base. Okay, it is a special salt called a base. And hydrochloric acid is an acid. So you can say that is an acid-base reaction. That's one of them. The other one is because it forms as carbon dioxide gas, you can also say it's a gas-forming reaction. Okay. It is also a type of ion exchange reaction. So ion exchange reaction would also work here. It is an ion exchange reaction. Okay, so you guys have done a couple of reactions so far, and that's kind of in the next section that we're doing today. But so I'll go through all of those reactions with you now. But any one of those, acid-base reaction, gas-forming reaction, or ion exchange reaction would work here. Our next one says calculate the number of moles of hydrochloric acid in 5 moles of hydrochloric acid if the concentration is 1 molar, 1 mole per cubic decimeter. Okay, there are 3 formula that you guys can use to get moles. Okay, your formula is from mass, your moles is equal to the mass over the molar mass. If you are dealing with volumes of gases, then the moles is equal to the volume of gas divided by the molar volume, which is a value of 22.4 if you're working at standard temperature pressure. Or if it's a concentration, then it's the moles divided by the volume. Okay, so those are the 3 formula that will get you to moles. Now, guys, generally, when you're doing any sort of stoichiometry or any sort of quantitative chemistry, finding the moles is usually the first step. So if they give you mass, find the moles. If they give you concentration, find the moles. Okay, finding the moles is generally step number 1. So they've given you here a volume, the 5 milliliters, and they've given you the concentration of 1 molar. Okay, so we're going to use our concentration formula. Concentration is the moles over the volume. The concentration is 1, and the volume, we need to take that to liter, so 0,005, and that gives you 0,005 moles. Right. The next one says calculate the mass of sodium chloride formed in the reaction in question C. So they're looking for the sodium chloride. Okay, you've got the moles of hydrochloric acid. Now, we always need to do a mole ratio first. I'm just going to move this over a bit. Okay, you always need to do a mole ratio. So when you do a mole ratio, we write it down nicely. We're going from the hydrochloric acid to the salt, NaCl. It's a ratio of 2 to 2 or 1 to 1. Okay, 2 to 2 is the same as 1 to 1. Now, we know that we have 0,005 moles of acid. We got that from our previous question. So we will have the same moles of sodium chloride, 0,005. Please note how I've written it down. Practice writing it down like that. First of all, it's going to then make sense in your head as well, and you won't use the wrong thing accidentally. Second of all, it's much easier to mark if you write it down nicely. I know this sounds like it's your teacher's problem and not your problem, But remember, in grade 12, you having your papers marked externally, and they aren't going to fish for marks the same way your teacher will fish for marks. So you really do want to write your papers down in a way that is the easiest to mark, that the examiner is going to make the fewest possible mistakes. So right from the beginning, learn how to write it down properly. Okay. It is your problem at the end of the day. Okay. You don't want people to be making mistakes when they're marking your paper. So now we have the moles of sodium chloride. We've used our ratio and we've checked, and we have the same moles of sodium chloride. They've asked us for the mass. So now we've got to use one of these three formula again to get the mass. That's going to be the first formula. So our moles is equal to the mass over the molar mass. The moles is 0,005. And the molar mass there is the molar mass of sodium chloride. For that, we need to go back to our periodic table. So let me just switch here quickly again. Okay, we've got NaCl, Na, our sodium, that has got a molar mass of 23. Chlorine has got a molar mass of 35,5. Right? So one of each, we're going to add that together, the mass number together, 23 plus 35,5. Okay, and that should give you 58,5. Right, so that molar mass there you get from your periodic table, right? We're going to add that together. Make sure that you're adding it for sodium chloride. We're busy working out sodium chloride. Now we times these two values together and we get the mass there, 0,29 grams. So I'm just reading the chat again, guys, just while you guys write it down. Masindi, your question there in the chat. So in the test, are you allowed to put the water on top of the arrow for dissociation reaction? Yes, it's actually preferable to put the water on top of the arrow for the dissociation reaction. It just shows that water is the solvent. The one thing that you mustn't do, though, is go sodium carbonate plus water gives you this and this and this. So don't add water in as a reactant. Just put it on top of the arrow just to show that that is your solvent. Okay. I know that in the IB, sorry, Cindy, I'm not sure if you're IB or GDE, but in the IB, they actually require that H2O on top of the arrow. I'm not 100% sure on the GDE, but it is better to put it in. Okay. All right, guys, does anybody have any questions on this question? We're going to take our break at past, by the way. Okay. Let's have a look at the next one here, question 1.2. Okay, question 1.2 says study the balanced chemical equation of the reaction between sodium carbonate and hydrochloric acid and answer the questions that follow. So we've got sodium carbonate plus hydrochloric acid gives you sodium chloride plus carbon dioxide plus H2O. Identify the type of reaction above. Choose between redox and gas forming. It is a gas forming reaction. Carbon dioxide is a gas, so it's forming a gas. It's a gas forming reaction. Okay, it's actually an ion exchange reaction, not a redox reaction. All right. In a reaction, we've got 10.6 grams of sodium carbonate reacts completely with excess hydrochloric acid. So we've got grams of sodium carbonate here. Okay, that one there. Now, remember, guys, when you're doing these things, you want to find the moles first. Okay, moles is very important to find, all right? So if you see grams, take it straight to moles. Okay, know that is, you're going to have to do that anyway. So that is pretty much step number one. Okay, our first question here, they've scaffolded this nicely. So in other words, they've broken it down step by step. The first one says calculate the molar mass of the sodium carbonate. So for the sodium carbonate, we've got 2 sodiums. So that we're going to take 2 times 23 for the sodium. We're getting this, these are our mass numbers of the periodic table, hey? Plus we've got 1 carbon, so plus 12, plus we've got 3 oxygens, so that's 3 times 16. All right, that there will give us a molar mass of 106 grams per mole. Okay, so that's the first one there. So 106 grams per mole. Now it says calculate the initial number of moles in sodium carbonate. So we've got the mass and we've got the molar mass. So we can get the moles, all right? We're going to use moles is equal to the mass over the molar mass. The mass is 10.6. The molar mass is 106. And that's going to give us 0.1 moles. Okay. So finding the moles generally the first step always. Now they're asking about the carbon dioxide. So they want to know, calculate the mass of carbon dioxide produced during this reaction. So we've got the sodium carbonate. We're looking for carbon dioxide. Those are the two that you're going to be using in your mole ratio. Okay. So in your mole ratio, you always use the one that you've got and the one that you want. So you pick out, it can be any reactants or products. Hey, if you've got information about any one, you can calculate information about any other one. So the two that we're using here is the one that we've got, the sodium carbonate, and the one that we want, the carbon dioxide. Right, so I'm just going to move this over a little bit. Okay, so our ratio here is a 1-to-1 ratio, but we're going to write it out anyway because it's a good habit to get into. So sodium carbonate to carbon dioxide is a 1-to-1 ratio. So if we have 0.1 moles of that, we will also have 0.1 moles of carbon dioxide. Okay, they want the mass of carbon dioxide. So now we've got to use our formula again. Oh, the moles is equal to the mass over the molar mass. So, oh, actually, wait, let me write it underneath here. The moles was 0.1. We're looking for the mass. And the molar mass of the carbon dioxide is 44. So we get the 44 from taking 1 carbon, which is 12, plus 2 oxygens, each one is 16. And that's what gives us the molar mass of 44. So we're using the molar mass of the carbon dioxide. That then gives us a mass of 4.4 grams. Keep in mind, guys, we work in grams in chemistry, kilograms in physics. Okay, so everything here is in grams. Okay, anybody have any questions so far? Benati, I'm just looking at your question here quickly. So would a redox reaction only happen when there is oxidation, or would it work the same as an ionic bond? I'm just trying to see what you're asking, but generally redox reactions, okay, so redox reactions, and we're going to talk about that in the next section in a little bit more detail again, but redox reactions happen when electrons transfer. So one substance must lose electrons and one substance must gain electrons. So there will always be oxidation and there will always be reduction. Okay, so redox reaction will only happen if there is oxidation and there is reduction. Okay, that's the only time you will have a redox reaction. So not just, I don't know if you talk about the ion exchange reactions, when the ions just swap around, it's not that. When the ions swap around, then there's no oxidation and reduction. It's about the charges, the oxidation states, okay, the charges on each element. If those charges change in any way, it's a redox reaction. But when they swap around, the charges don't actually change. That's why it's not a redox reaction. So yeah, so the ion exchange reactions are different to redox reactions. They're not the same thing. I hope that answers your question. Okay, cool. Okay, guys, I think there is one more here. So we can do one more. So calculate the mass of sodium chloride produced if 4.8 cubic decimeters, so this is a liter, so we've got 4.8 liters of carbon dioxide was produced at standard temperature pressure. So we're looking at the sodium chloride and the carbon dioxide. We're looking at these two because they're giving us information about the carbon dioxide and they're asking us information about the sodium chloride. Okay, so you're always going to use the one that you've got information on and the one that you are looking for. All right, so let's start over here. We're going to start by using that carbon dioxide. They've given us a volume. What was it again? It was 4.87 liters at standard temperature pressure. Now, your first step, find the moles. The formula you're using here is moles is volume over molar volume, okay? Because you're working with a volume of a gas at standard temperature pressure. If you see STP, you must see the number 22.4 blinking in your mind, okay? STP goes with 22.4. That's the molar volume of gases at standard temperature pressure. So the total volume there was 4.87. And now your molar volume at standard temperature pressure is 22.4. And that gives you 0.217 moles. Right? Now, they've given you, this is the carbon dioxide. They're looking for the sodium chloride. So we're using carbon dioxide and sodium chloride. You must always do your mole ratio. Now, in this one, we've got 1 carbon dioxide and 2 sodium chlorides. So we have a ratio of 1 to 2 here. 1 carbon dioxide, 2 sodium chlorides. So if you have 0.217 moles of carbon dioxide, 1 to 2, so you will have double the number or the amount of sodium chloride, so 0.434 moles. Okay, guys, these mole ratios, please stick to whichever method of ratios that you know that you like to work with. I like to work with a method that says if you write it down like this, then you take what you've got, you divide up, so divide by 1, and where's my arrow go? And you times across. Okay, so divide up times across, divide by 1 times by 2. So if it was a ratio of 2 to 3, you would divide by 2 times by 3. Okay, divide by the number above times by the number across, and that gives you the new number. Please use whichever method you feel more comfortable with, but that's the way I do it. Okay, we're not finished yet. They want the mass of the sodium chloride. So our last one here, our mass is equal to the moles times the molar volume. The moles is 0.434. Molar, what did I say? Molar volume. The molar mass. The molar mass, we're looking at the molar mass of sodium chloride. So here we're taking 23 for sodium plus 35.5 for chlorine. And that's going to give us 58.5. So times 58.5. And that gives us a mass of 25.16 grams. Now, guys, I don't know if all of you are this far yet. Please just let me know if there is anything in this section that you would like me to go over a little bit slower or give you extra examples of. So just shout, okay? All right, so I'm going to go through them nice and slowly. Aqueous solutions. Now, we can dissolve substances in just about, a couple of different substances. There are a lot of substances that can act as solvents, right? You can dissolve sugar and vinegar would be your solvent. An aqueous solution is a solution where specifically water is the solvent. So when we have that little AQ subscript at the back of a substance, so if we talk about let's say I don't know why I did that, HCl, and then we put the little aqua sign next to it. That aqueous means that this HCl is dissolved in water. Okay, it means that water is specifically the solvent. So that's what an aqueous solution is. Now, water is a polar solvent, and polar solvents can only dissolve other polar substances or ionic substances. In other words, oil doesn't mix with water because oil is not polar. Okay. It's a like dissolves like thing. Now for the IB guys, this doesn't really come into your syllabus at all, but the GDE guys, this will definitely come into your syllabus. And anyway, it is a good thing to know. Like dissolves like. Polar substances dissolve in polar substances, non-polar substances dissolve in non-polar substances. Now, for example, the reason why oil and water don't mix, the polarity in water, in other words, the fact that water has this end that is quite negative and the other end that is quite positive, it gives it poles. Now, because of those poles, the water molecules actually hold on to each other quite strongly. This is why the surface tension of water is relatively high. The boiling point of water is relatively high. It's because of these poles. Now, oil, not having these poles, is unable to separate the water molecules from each other. The water molecules are actually holding onto each other very, very tightly. So oil can't get in there and separate the water molecules, and that's why it doesn't mix. But any substances with poles will be able to do that. They'll be able to get in there and separate these water molecules from each other. The poles give a little bit of extra electrostatic force and are able to separate the forces between the water molecules. So ionic substances will dissolve in water depending on how strong that ionic bond is. If the ionic bond is too strong, then the substance is generally insoluble. The water is unable to separate the ionic substance into its ions. Now, there is a table of solubility rules that you guys need to know. So you do need to know those solubility rules. And that's why some substances are just harder to separate from each other than others. And if water is unable to do that, then these substances are insoluble in water. Okay. All right. So water molecules pull the ions free from the ionic crystal, and this is called dissolution. Okay. The ions become totally surrounded by water molecules, and that is called hydration. So you actually need to separate an ion into, or an ionic substance into its different ions. You actually need to surround the ion with water molecules. It doesn't just take one water molecule to separate ions from each other. It takes a whole lot of water molecules. So in this image over here, you can see that if you have a positive ion, it's generally the negative side of the water molecule that surrounds that positive ion, and a whole bunch of water molecules will pull it away. If you have a negative ion, like on the other side, it's the positive ends of the water molecule that surround it, and those positive ends will pull the negative ion away. So you do need far more water molecules than the salt to dissolve that salt. If you run out of water molecules, you will stop being able to dissolve the salt, and then we say that the solution is saturated. So when you're not able to dissolve any more salt into your solution, we say it's saturated. And it just means that there aren't any available water molecules to separate the salt into its ions. Okay, dissolving of ionic substances. So water molecules are attracted to each other and to ionic compounds with the oxygen end, that's a negative sign closest to the cation, the positive ion of the salt, and the hydrogen, which is the positive end, which is closest to the anion, the negative ion of the salt. This little delta sign, so delta negative and delta positive, that sign means slightly. Okay, so if you look at your water molecule, one end is slightly negative, one end is slightly positive. That's what that delta sign means. Okay. So the positive ends of the water surround the negative ions, and negative ends of the water surround the positive ions, and it pulls them away, separates them, and then they separate from the crystal lattice, and they are in aqueous phase. They turn into aqueous phase. So this example over here, dissociation of NaCl, it's in a solid phase initially. This is dissolving salt in water. We like to put our water at the top here to show that it is the solvent. And then we have Na+ ions in an aqueous phase and chloride ions in an aqueous phase. Guys, watch your language. It's not a chlorine ion, it's a chloride ion. The negative ions become ides. So a sulfide ion, an oxide ion, a nitride ion. Just watch watch the negative ions, okay? They become ides. It's not correct to talk about a chlorine ion. It's a chloride ion, okay? I think the most difficult thing about chemistry is the language. You have to be very careful when you use your language in chemistry. Language is marked down more than anything else in chemistry. In other words, like, for instance, if you're talking about the particles, you've got to choose which kind of particle it is carefully. Water is a molecule, and salt consists of ions. You got to really choose the correct word and match the correct words all the time, because if you use the incorrect word, obviously then the science is wrong, and they're very strict on that. So all the way through your chemistry, watch your words choice. Okay, next one. If you have these aqueous solutions that have ions in them, okay, so ionic substances that dissolve in an aqueous solution, then that becomes an electrolyte. An electrolyte is a solution that contains ions, free moving ions, and it is able to conduct electricity. Guys, when we say it's able to conduct electricity, it's not that something moves from one side to the other. The electricity doesn't really move through the solution, okay? It doesn't really work that way. What you end up having is, so for instance, over here, we've got two electrodes. The electrodes are the sticks, okay? They are placed into the aqueous solution. The electrons will move around the external circuit. So here in the external circuit, you will have electron movement from the one to the other. But here in the solution, you actually have ions migrating towards the electrodes. So something like that, okay? You'll have ions migrating towards those electrodes, for instance, but it doesn't really flow through the solution. The ions just give off electrons and receive electrons in the process. Now, the more ions you have, the better the solution conducts. Okay. All right, so that is an electrolyte, a solution containing ions that is able to conduct electricity. So now we're going to start looking at our ion exchange reactions. Now, some ion exchange reactions will give you a precipitate. A precipitate is a solid forming out of a solution. So you have a solution, everything is dissolved, you can't see any solid bits, but then you add a substance and all of a sudden a solid sinks down to the bottom. It's a very fine powder solid, so it's not like a lump that just gumps at the bottom. It's a very fine powder that starts to form, and that is an insoluble solid that starts to form. That solid forming from a solution is called a precipitate. Okay, so precipitation reactions is the one kind of thing that can form in an ion exchange reaction. The other thing that can form in an ion exchange reaction is a gas. Now, we had a look at the gas forming reaction briefly now, but I'll show you now how that is also an ion exchange reaction. So precipitation reactions, anions and cations bond with new partners to form insoluble salts. Okay, so in an ion exchange reaction, let me just go to another screen here quickly. Just get this concept down first. Okay, in an ion exchange reaction, you have a positive ion bonded to a negative ion, okay, and then you add in a substance that has also got a positive ion and a negative ion. Now, at the end of this reaction, the positive ion from the one will bond to the negative ion of the other one, and the negative ion, the positive ion of the other one will bond to the negative ion. The other one. That's why I say they swap partners. Okay, so if the blue ones were partners initially and the red ones were partners initially, they swap partners. Okay, so the ions, the anions and the cations will swap around. Now, when that happens, one of these might be insoluble. It forms a new substance that might be insoluble. If everything's soluble, it's not really going to give you a very noticeable change in your reaction. Everything will just still be in solution. But if they swap around and one of them's insoluble, form something that doesn't dissolve, then you'll see it. Okay. A lot of the time, the most common one is when you form silver halides. So silver iodide, silver chloride, silver bromide. Okay, those silver halides are generally insoluble, okay, and they form these precipitates. I think you learned these ones with colors as well. The chloride is white, a white precipitate. The bromide is a creamish color precipitate, and the iodide is a yellowish precipitate. So it can form substances that you will see if those substances are not soluble. Let's have a look at the gas forming reaction quickly. So if you have, what did we say it was? Carbonate and an acid. So let's say we've got the sodium carbonate. It was this one here. I'm going to show you how this is an ion exchange reaction. Plus the HCl. Okay, now the positive ends here swap around. Okay, so you've got sodium here as a positive end and hydrogen there as a positive end. That's going to give you, if you swap those positives around, it gives you H2CO3 plus NaCl. Okay, please, when you swap it around, make sure that you do the formula properly. You always have to look at the crossover method and get the ratios of the atoms properly. Okay, you can't just go, there's 2 sodiums here, so I need 2 sodiums there. You would balance this equation out. Okay. So balancing happens at the end. Your sodium chloride is in a ratio of 1 to 1. It's not 2 sodiums because you had 2 sodiums initially. So careful for that. You must re-look at these ratios every time. Now, I said that this was a gas forming reaction, but where's the gas? So what happens is that it's an ion exchange. The hydrogen and the sodium have swapped around. But this hydrogen carbonate that forms, this substance breaks down and forms H2O and CO2. Okay, so that hydrogen carbonate decomposes into water and carbon dioxide. So it is initially an ion exchange, and then the hydrogen carbonate decomposes into hydrogen and carbonate, and that is where we get our gas from that carbon dioxide that forms. So it is ion exchange, and then it is gas forming because the hydrogen carbonate will decompose. Right. Does anybody have any questions on this? Oopsie. Okay, any questions on this, guys? You're right. Okay, if you want me to come back to this now, we can as well. Okay, let's go back to the slides. Right, so the precipitation reactions are the ones where the 2 substances, the new pair, will form a solid, an insoluble salt. Precipitation reactions can be used to test for the presence of certain anions. So if you want to test for a halogen, then you would add a silver nitrate. Okay, so silver nitrate is the test substance because it's going to give you that silver bromide, silver chloride, silver iodide. Okay, if you want to test for a sulfate, you would add barium. No, it's for a carbonate. You would add barium something. I can't even remember right now. Barium something. I can't remember what it is. Maybe one of you guys remember offhand. I haven't looked at this in a while, but barium chloride. Yes, yes. Okay, so that would be the test substance because barium will form an insoluble salt with your sulfate ion. Okay, so so it is the barium chloride. You form an insoluble salt with your sulfate ion. Then the test for a carbonate, that one you add your acid because the acid will give you the gas forming reaction. And the gas forming reaction, if you see those bubbles, you know that there was a carbonate. Okay, the carbonates and acid will always give you that carbon dioxide. So because these certain things give you a reaction that you can predict, we can test for these anions, these negative ions, using these ion exchange reactions. Okay, Cindy, okay, good question. So in the precipitation reactions, would they give you the reactants so that you swap the partners? Or how would they ask it? Okay, so there's two ways that they can ask it. Yes, that is the one way. They can give you a reaction and say, substance A reacts with substance B, what are the products? You swap around the partners, and then you've got the products. Okay, so that is the one way that they can ask it. The other way that they can ask it is with the test for the anions. So they can say, we're testing for a chloride ion. What would you add? That you have to learn. So you got to learn, if you're testing for one of your halogens, your chloride, your bromide, your iodide, then you're adding silver nitrate. If you're testing for a sulfate, you're adding barium chloride. If you're testing for a carbonate, you're adding an acid. So adding those three tests is theory that you need to know. And then you're going to do the swap over and get the product. But that's the only time that you'll have to guess what the other reactant is. Well, not guess, but study what the other reactant is. Otherwise, they will give you both reactants and you swap around and give the answers. Okay. Okay. So types of ion exchange reactions. I just want to put here this first one. It is a reaction with an acid. All of these are reactions with acids, but this first one, guys, is not an ion exchange reaction. It's a redox reaction. So please just make that note there for yourself. That first one is actually a redox reaction, not an ion exchange reaction. Okay. Now, these general reactions with acids, this, Cindy, also is another way that they could ask it, okay? Because these general reactions, you do need to know what the product is going to be here. So you need to know what this gives you. You need to know acid and a metal is going to give you a salt and hydrogen gas. An acid and a metal oxide is going to give you salt and water. An acid and a metal hydroxide is going to give you salt and water. And an acid and a metal carbonate is going to give you a salt, water, and carbon dioxide. That you need to know off by heart, okay? Figuring out the salt is what you will do depending on what the acid is and what the metal is in the metal oxide or metal hydroxide. So let's talk about that quickly. This salt, how do you get the salt that forms in each of these? Okay, I'm going to go back to now the screen quickly. All right. A salt forms when you replace the hydrogen of an anion or of an acid with a cation. Okay, so if we take our acids, HCl, H2SO4, H2CO3. Okay, we've got hydrochloric acid, we've got sulfuric acid, we've got carbonic acid. These are just some of the acids. Okay, so if you take the hydrogen and replace it with a cation, then you form a salt. Now, what is a cation? A cation is a positive ion. Generally, it's going to be here the metal ion. Okay, so we're going to take the hydrogen away and replace it with a metal ion. So if you're reacting an acid with a metal, like let's say magnesium, then the magnesium takes the place of the hydrogen. Okay, and that is your salt. Please do the crossover method properly. You have to get these ratios properly. Magnesium is 2+, chloride is 1-. When you do the swap over, it gives you this formula. Okay, if you don't know how to do this, make a note and right at the end we can go over it. Okay, if there's anybody who still doesn't know how to do this, I'll go over it at the end, but just make a note now. Okay, and then hydrogen gas. How do I know hydrogen gas forms? Because I know that an acid and a metal gives me a salt and hydrogen gas. I know the general formula, and from the general formula I can predict what products are going to form. Our next one here, so let's say we've got sodium hydroxide. So an acid and a metal hydroxide, the salt. If I take my metal and swap it with the hydrogen, I end up getting Na2SO4 and water. How do I know water forms? Because I know that an acid and a metal hydroxide gives me a salt and water. How do I get my salt? I take the metal and I put it in the place of the hydrogen. Okay, you swap the metal and the hydrogen, that gives you the salt. If I say the carbonate here, the hydrogen, the carbonic acid, let's say we react carbonic acid with a metal oxide. Actually, this is a bad example. The carbonate is a bad example. Anyway, let's do it with a metal. Okay, so let's say I reacted with lithium metal. How do I get my salt? I replace the hydrogen with the metal. So that's going to give me lithium carbonate and hydrogen gas. How do I know it gives me hydrogen gas? Because an acid and a metal gives me a salt and hydrogen gas. Okay. Guys, I hope that makes sense. So that's how you get your salt. The other product, you know, because you've learned the general reaction. Okay. Go back to the slides. So here in this example, metal hydroxide plus an acid gives you salt and water. This metal hydroxide is sodium hydroxide plus HCl. The sodium takes the place of the hydrogen, giving you your salt, NaCl. And then water forms, you know, because a hydroxide and an acid gives you a salt and water. Okay. So that's those ion exchange reactions. All right, then the gas forming reactions we've looked at already. It's ion exchange initially, and then the hydrogen carbonate breaks down and gives you water and carbon dioxide. So in this one, we've got sodium carbonate and the HCl. The sodium chloride is the salt. So sodium takes the place of the hydrogen, giving you the salt plus water plus carbon dioxide. Okay, our tests for gases, just a quick recap on this. I think you probably did this in grade 9. Test for hydrogen gas. A splint will ignite with a pop sound, makes it pop sound. Test for oxygen gas. If you have a glowing splint that hasn't got a flame and you put it in oxygen gas, it will ignite and to give you the flame. Carbon dioxide will turn lime water cloudy. Okay, so those were the 3 tests for those gases. Just a quick recap on that. So this one, obviously forming the carbon dioxide, you would look at the test for the carbon dioxide. The first one, the acid and the metal forming hydrogen gas, you would look at the test for hydrogen gas. Okay, now we're looking at our redox reactions. So the redox reactions are not ion exchange reactions. Okay. In a redox reaction, you always need reduction and oxidation. Redox is a transfer of electrons. Electrons transfer from one substance to another substance. Okay. When that happens, one substance obviously loses the electrons and the other substance will gain the electrons. That's why you always need both processes. You need oxidation and reduction to occur in a redox reaction because the electron must come from somewhere and it must go to somewhere. So you can remember this. So the reduction is the gain of electrons. Okay, reduction is gain. Oxidation is the loss of electrons. Oil, oxidation is loss. So we've got oil rig. Okay, remember oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Use that to remember which one's which. So the substance that loses its electrons, we say that substance is oxidizing because it's losing the electrons. And then the substance that gains the electrons is reducing because it's gaining the electrons. Now, this seems bizarre because how can something reduce, but it's gaining? Because doesn't the word reduce mean getting smaller? And if you're getting smaller, how can you be gaining electrons if the word reduce is getting smaller? I don't know if this confused you guys, but there's another way of looking at it that makes a lot more sense. Okay, if you look at something like magnesium 2+ that gains electrons and forms magnesium neutral, magnesium 0, okay, instead of looking at the gaining of the electrons and the losing of the electrons, look at the oxidation state. This oxidation state has gotten smaller. It was +2 and now it's sitting at 0. Okay. Do you guys see it? This is why it's called reduction. This is what's reducing. It's the oxidation state that's reducing. So something is getting smaller. It's the oxidation state that's getting smaller. Another example is if we take chlorine gas and we add 2 electrons to form 2 chloride ions, okay? Look at the oxidation state here. The oxidation state initially is 0, okay, because 2 chloride ions bonded together gives you an oxidation state of 0. It's a neutral substance. So 0, and now it's -1. So the oxidation state has gotten smaller. The charge has gotten smaller. That's what's reducing. So gaining those electrons makes the charge smaller. All right. So it does make sense if you look at it properly. All right. So that's reduction. Reduction, gaining the electrons, the oxidation state becomes smaller. The oxidation is then going to be the loss of electrons. So you can imagine that the opposite would happen if something's losing electrons. The oxidation state will become bigger. So you could have something like Fe2 plus is going to give you Fe3 plus an electron. Okay, it's losing the electron. The electron is written on the product side. It's being lost. It's being given off as a product. And when it does that, the oxidation state increases. Okay, it's gone from 2 plus to 3 plus. It's become bigger. Think about it this way. If you gain negative things, you become a negative person. So if you take in something that's negative, you become a negative person. So if you're taking in negative electrons, your oxidation state is going to become more negative. Okay, if you give off everything that is negative in your life, if you get rid of everything that is negative in your life, you're going to become a much more positive person. So if you're giving off the negative electrons, then the oxidation state is going to become more positive. Okay. All right. It takes concentration. So when you get to this, slow down and look at it carefully. All right. Oxidation is the loss of electrons. Reduction is the gaining of electrons. Both processes need to happen in a redox reaction. And in a redox reaction, these ions, the state, this oxidation state changes, the charge changes. In a ion exchange reaction, they don't change. That's why an ion exchange reaction is not a redox reaction. Okay, I'm going to go back to the slides. So in this example here, hydrochloric acid reacts with zinc to form zinc chloride and hydrogen gas. This is the one with an acid and a metal gives you a salt and hydrogen gas. Remember I said in the previous slide, this is a redox reaction. So what's happening here? We've got hydrogen, which is H+. We've got chloride, which is Cl-. We've got zinc that's standing alone, so it's zinc 0. Then zinc bonds to chloride, and in this, you can do the reverse crossover if you're not sure about the oxidation states. It becomes zinc 2+ and chloride -1. And then hydrogen, anything bonded to itself is an oxidation state of 0. So it becomes H0. Okay, so its oxidation state here is 0. If it stands alone, its oxidation state is 0. So the zinc alone, the hydrogen gas alone, oxidation state is 0. Okay, so now look at how these charges have changed. Do you see, first of all, that the chloride ion has not changed? The chloride ion is -1 and -1. We call that a spectator ion. Okay, it's spectating. It's not taking part in the reaction. It's not part of the reduction and the oxidation. So it's spectating. It's a spectator ion. Now the others, we've got hydrogen that's gone from H+ to 0. Ask yourself, has its oxidation state gotten bigger or smaller? It's gotten smaller. It's gone from +1 to 0. So it's reduced. Okay, so the hydrogen is going to reduce. Look at the zinc. The zinc's gone from 0 to 2+. Ask yourself, has that oxidation state gotten bigger or smaller? It's gotten bigger. If it's gotten bigger, it's oxidized. oxidation is the loss of electrons. So the zinc is losing electrons for its oxidation state to become bigger. Right, so now we write them into our half reactions. So here's our zinc half reaction. The zinc 0 is becoming zinc 2 plus, and it's oxidizing. So it's losing electrons, 2 electrons. The hydrogen is busy reducing. It's going from positive to 0. Okay. It's gaining electrons, and you just balance the equation out here. You've got 2 hydrogen atoms on the right, so 2 hydrogen ions on the left, and therefore a total of 2 electrons are gained. So the 2's there are just the balancing out. Okay, guys, when you write these half reactions, it's very important that you always use a single arrow. I don't know if any of you guys have seen double arrows or if you use a double arrow as an arrow that's forward and reverse. But half reactions, we only use a single arrow always. Does anybody have any questions on this? Okay, we've got to the end. So no questions? Are you guys happy? Okay, can we do the practice then? Let's have a look at some of the questions here. Right, where were we? Okay, question number 2. So we're going to start here at number 2.1. Now, this one's going to talk about the sorry, I'm trying to move this page. Where's my thingy, my bob here at the bottom? Here it is. There we go. Okay, so our first one over here is going to just talk about those properties of liquids, solids, and gases. So this is just a table to fill in. So we're going to do this one quickly. Oh, Masindi, okay, I'll go through the oxidation and reduction again. I'll do another example with you guys. Let's do this question number 1, and then I'll do another example of oxidation and reduction. Cool. All right, so our first one here, the gas. So when we look at the shape of gases, gases generally fill the container. So that will depend on whatever the container shape is. The forces between particles in a gas are very, very weak / no forces. Okay, we actually, an ideal gas we will consider as having no forces between the gas particles. The arrangement of the particles, there is no specific arrangement. They move around continuously, and they are very far apart. There are large spaces between them. They're very far apart, and they move around randomly. The movements of the particles very fast. They move in all sorts of directions. Okay, the liquid, the volume of a liquid, that's a fixed volume. So liquids, where gases will fill the container and the volume of the gases will fill the container. So the volume of the gas is dependent on the volume of the container. Liquids will always obviously lie in the bottom of the container, so they have fixed volumes. The shape of a liquid, it will take the shape of the container, so that also depends on the container. The space between the particles, there are small spaces between the particles, but less than gases, obviously. The forces between the particles, there are weak forces between the particles of liquids. The arrangement of the particles, it's random, they roll over each other, they are in contact with each other though. The movement, they slide past each other. Okay, then the solid, its volume is also a fixed volume. So it doesn't depend on the container, but it's a fixed volume for a solid. Shape is also a fixed shape. So solids can come in many different shapes, and it will hold its shape. Okay, that's the important part. It holds its shape. It's not dependent on the container. Spaces between the particles, very, very, very small spaces between the solid particles. The arrangements of the forces between the particles of a solid are strong forces between the particles of a solid. And the movement is just a vibration. Okay, number B says sodium and chlorine are very dangerous elements in their pure form. Table salt contains these two elements, but it is safe to eat. Explain. You're looking at different substances with different properties. Sodium, Na, and chlorine, Cl2, chlorine gas. Those are substances with their own properties, okay? But when they react with each other, they change, and chemical change takes place. And when you have sodium chloride, sodium in its ion form and chloride in its ion form, then it forms a new substance with new properties. Okay. So the one of those new properties is now, it is good for you in very small amounts, not harmful anymore. All right. Any questions on that? Okay. I'm going to go to the other screen quickly and just quickly first do another example on oxidation and reduction. Okay, so let's have a look at this example. Let's say sodium reacts with zinc. Let's make it zinc nitrates in O3. Okay, and a 2 there. Okay, and this is going to give us zinc and sodium nitrates. Okay, we need a 2 over here to balance and a 2 over there to balance. All right. Okay, so let's have a look at this example over here of a redox reaction. Okay, so remember I said that if the substances are alone and they're not bonded to anything, then their oxidation state is 0. So they have a charge of 0 by themselves. In this substance, our zinc nitrate has a charge of -1. How do you know? Because you've learned your list of complex ions and nitrate is one of them. So NO3 -1 is the charge on a nitrate. The zinc, you can do a reverse crossover method and you'll find that zinc has a charge here of 2+. Zinc over here has a charge of 0 because it's in its it's standing alone, it's not bonded to anything. Sodium over here has a charge of +1, and the nitrate's still a charge of -1. So the nitrates, first of all, are the spectator ion. They don't change. The oxidation state stays the same. All right, so spectator ions. So we're looking at the zinc and the sodium. Okay, let's look at the sodium first. Sodium has gone from sodium 0 to sodium +1. So sodium 0 to sodium +1. That oxidation state, has it gotten bigger? Has it gotten smaller? Okay, it's gotten bigger from 0 to +1, so it's oxidized. Because it's oxidized, it's the loss of electrons. When we do loss of electrons, we write them on the right-hand side as a product. Okay, when it loses electrons, it's written on the right-hand side as a product. The zinc going from 2+ to 0. Okay, what has happened to zinc's oxidation state? It's gotten smaller, it's reduced. Okay, so if you look at that oxidation state, 2+ to 0, it's reduced. The reducing means gain of electrons, RIG. Reduction is gain. So the Zn2+ is going to gain electrons, and it's 2 electrons. All right, and that's going to form zinc 0. We don't write the 0. Okay, we just leave it off. It's just 0 is just like that. So we don't really write 0. So here we have our oxidation reaction in the green, and in the pink, our reduction reaction. Okay, if you want a net ionic reaction, so the two together, I don't know how many of you guys have gone this far, but if you do want the two together, the electrons need to balance. The amount of electrons given off needs to equal the amount of electrons taken up. So you would have to times this through by 2 to get the electrons equal. And then the electrons cancel and you write down everything on the left. And everything on the right. Oopsie, plus. Okay. That's for the net ionic equation. Okay, you just get the electrons to balance for the net ionic equation, and you just write down everything on the left, everything on the right with the electrons cancelled out. So I don't know if you guys have gone that far, but those of you who have, that's what you're looking at. Okay, how do you guys feel about this? Is it okay? Must I do another one? Okay, good. All right, good. This is a tricky chapter, guys. This is not fun. I promise you. I know, and especially in grade 10, it does get better though. Okay, there is a request for one more. So let's do one more. It is I think probably the hardest part of this whole section today. So let's do one more. There is a request for one more. Okay. Let's do, think of one off the top of my head. Let's do okay. Let's do iron chloride. Racking my brain here, guys. Plus magnesium is going to give you magnesium chloride plus iron. Okay, there we go. Okay, let's see. So let's first put in an oxidation state here. The iron over here is an iron 3+. Do you guys see that? Chloride is -1, iron is 3+. It's the reverse of the crossover. So chloride is -1, iron is 3+. Okay. Magnesium is alone, so it's 0. Here, if you do the reverse of the crossover method, you'll find the magnesium is 2+, the chloride is -1. And the iron is alone, so it's 0. All right, so those are our oxidation states. So now we have a look here. Do you see anything special? Yes. The chloride ion has stayed the same. So it is a spectator ion. It has not changed. Okay, so we're going to look at the other ones. So the iron has gone from 3+ to 0. Okay, what's happened to its oxidation state? Has it gotten bigger? Has it gotten smaller? It's gone from 3+ to 0. It has gotten smaller. So it has reduced. So this is reduction because the iron 3+ is going to change to iron 0. Okay, when that happens, what happens? It gains electrons. Remember, it's reduction. So it's gaining electrons and it's gaining 3 electrons. Okay, 3 positive plus 3 negative is going to give you a total charge of 0. All right, let's look at the magnesium. Magnesium has gone from 0 to 2+. What's happened to its oxidation state? It's gotten bigger. Its oxidation state gets bigger, it means it's oxidizing. If it's oxidizing, it's losing electrons. Oxidation is loss. So we've got magnesium 0, giving you magnesium 2+, and losing 2 electrons. Okay, so you've got your reduction at the top, the gaining of electrons, reduction at the top, the loss of electrons at the bottom. Now, if you have done the net equation, the net ionic equation, you need to make sure that the electrons balance. We've got 3 electrons being gained in the reduction, and we've got 2 electrons being lost in the oxidation. These two values need to be the same. So our lowest common multiple is 6. So if we times this by 2, we will get 6, okay? But we need to times throughout by 2. So now we've got 6 electrons there. If we times this one by 3, we will get 6, but we need to times it throughout by 3. Now we've got 6 electrons, 6 electrons. So they cancel and we write down everything on the left. 2 Fe3 pluses plus 3 magnesiums, and everything on the right. 2 ions plus 3 magnesium 2 pluses. Okay, does that help? Okay, it's a tricky chapter. Guys, it won't be tricky forever. It will get better. All right, you do this again a little bit in grade 11, you do it again a little bit in matric. Okay, so it does get better. But right now, it's hard. Okay, I'm not going to try and sweet talk that one for you. It's a hard section right now. Okay, let's do question 2.2. When methane reacts with oxygen, water, and carbon dioxide are formed. Okay, so this reaction is a very special reaction. If anything reacts with oxygen, an organic compound reacts with oxygen, it always forms water and carbon dioxide. This is a combustion reaction. Okay, and there are tons of combustion reactions. You can literally take any organic compound and react it with oxygen and you'll get water and carbon dioxide, always. So the products are always water and carbon dioxide. Doesn't matter what compound you start off with. Write a balanced equation for this reaction. So let's see, we're starting with methane, CH4. It's reacting with oxygen and it's forming water and carbon dioxide. Okay, so that's pretty straightforward, but now we need to balance this. So you're going to count your carbons on the left. You've got 1 carbon on the left, and you've got 1 carbon on the left, 1 carbon on the right. So carbons are fine. 4 hydrogens on the left, 2 hydrogens on the right. So if we times this by 2, we get 4 hydrogens on the right. So hydrogens are now balanced. Oxygens, 2 oxygens on the left, 2 times 1 is 2 oxygens on the right. So oxygens are also balanced. So that one's fine as well. Oh, no, sorry, I'm lying to you. Whoa. 2 oxygens there plus 2 oxygens there. Sorry, I missed that. 2 oxygens there gives you 4 oxygens on the right. Okay, so oxygen not balanced. We need to times this one by 2. Now it is balanced. Now we've got 4 oxygens on the left, 4 oxygens on the right. Guys, when you balance these reactions, these combustion reactions, always do the oxygen at the end. So fix the carbon and the hydrogen first, and then do oxygen at the end. Okay. The change is, okay, they want to know what is it, chemical or physical change. This is a chemical change, right? You're forming new substances with new properties, so it is a chemical change. Represent the reaction by drawing pictures of the molecules involved. I will leave the pictures up to you guys to do. So that's just drawing a picture of a methane and oxygen, a water and a carbon dioxide. Okay, I'll leave that one for you guys. How many oxygen atoms are there in one oxygen molecule? An oxygen molecule is O2. So there are 2 oxygen atoms in one oxygen molecule. Okay. This is the one that is very similar to the one that was in the slides. So the word equation is going to be the methane plus oxygen. Okay, so I'm going to fit this in. Methane plus oxygen. Oxygen, and that's going to give you water and carbon dioxide. Okay. So that's for the first one. That's your word equation. All right, the chemical equation is the one that we've got over there. So we've already got the chemical equation. If you count the atoms, we've got 1 carbon atom on the left. We've got the 4 hydrogen atoms on the left, and now we've got 4 oxygen atoms on the left. On the other side, we've got 1 carbon atom, 4 hydrogen atoms, 4 oxygen atoms. If you do the mass, if you add these all together, we find that we've got 1 carbon, so that's 1 times 12, that's the molar mass of carbon, plus 4 hydrogens, the molar mass of hydrogen is 1, plus 4 oxygens, so that's 4 times 16 is the molar mass of oxygen, and that gives you 80. and it's exactly the same on the right. So you also get 80 on the right. And that is just there to prove that your reaction is balanced. You have the conservation of matter. The mass before the reaction is equal to the mass after. Oh, oops, I went too far. Sorry. There it is. Oh my gosh. Sorry, I tried to reset the speed of this touchpad with the scrolling before the lesson started, and it doesn't. It's something in this app that doesn't allow you to change the speed of the scrolling, and I'm so used to scrolling on the touchpad, and I forgot I mustn't do that here because it just like goes, and I have no control over it. It goes way too fast. So sorry, I lost it there for a sec. Okay, let's do number 2.3, guys. This is the last one for today, and then the floor is open for any questions that you guys might have. All right, so let's do this last one quickly. This one says that Tabo burns a piece of magnesium which has a mass of 1 gram. He weighs what is left and found the mass was 1.8 grams. What type of chemical reaction has occurred? Now, if anything burns in oxygen, then it is a combustion reaction. Okay, so the magnesium is reacting with oxygen. Its mass is increasing. It started with 1 gram and ended up with 1.8 grams. So the mass increased somehow. That doesn't just, it's not magnesium that was multiplying. It bonded to something. And that bonding was to oxygen. Okay, so it bonded to oxygen. It is a type of combustion reaction. You can also say it's an oxidation reaction. So yes, oxidation is the loss of electrons, but when something reacts with oxygen gas, it's also oxidation. Okay, so combustion or oxidation. How can we explain this? Well, by the gain of mass. That the gain of mass had to come from something. So it's not just from the flame or from the magnesium, it's from the air. It bonded to the oxygen in the air to form a magnesium oxide. Okay. Question B says, when lightning strikes, a huge amount of energy is transmitted through the air. Nitrogen molecules react with oxygen molecules to form the different nitrous oxides. Draw Lewis diagrams for oxygen and nitrogen. Now, this question is a little vague because it hasn't quite specified if they want an oxygen atom or an oxygen molecule. Okay, so your memo has got the oxygen molecule, so it should have said maybe for oxygen gas and nitrogen gas, just to be a little clearer, because this could be interpreted in 2 different ways. So if you guys were wondering how you know, no, actually the question should be a little bit clearer. They should say an oxygen atom or oxygen gas. Okay, there are definitely 2 interpretations for this. Now, your oxygen molecule is with 2 oxygen atoms. Now, if you look at the oxygen atom, each atom has got 6 valence electrons. The valence electrons, guys, are the outer electrons. I'm just going to go back to the periodic table here quickly, just to show you how we get that. So if we label our group numbers 1, 2, skip 3, 4, 5, 6, 7, 8. If we work with our group numbers 1 to 8, then these group numbers are the number of valence electrons for our atoms. So oxygen over here will have 6 valence electrons. The nitrogen would have 5 valence electrons. Okay, so that's where we get that information from, right? The group number on the periodic table. Right, so this oxygen has 6 valence electrons. So we're going to go 1, 2, 3, 4, 5. I'm going to put it here so I can leave those 2 empty. And we've got another one, another oxygen, 1, 2, 3, 4, 5, 6. Okay, so when we do now the bonding, if these 2 bond together, it's going to be those 2 electrons that share and those 2 electrons that share. So because you have 2 shared electron pairs, then it means that you will have a double bond. Okay, for each electron pair that shares an orbital, you have a bond. So it will give you a bond with those 2 and a bond with those 2. The nitrogen was in group number 5. So 1, 2, 3, 4, 5, and another nitrogen, 1, 2, 3, 4, 5. Okay. Now, when these ones, you've got 3 available on each that need sharing and need pairing. So we can pair those two. We can pair these two. And we can pair those two. Okay, that looks terrible. So let's redraw that and draw it a little bit neater. We've got nitrogen, nitrogen. They make 3 bonds. And they've each got that little lone pair on the other side. Okay, so I've just shifted them around a little bit so that we can see our 3 bonds there. So a triple bond between nitrogen. Okay. All right, number 2 says, what does the first ratio between the molecules show? So that's this ratio over here. Those ratios, that's the molar mass. Okay, the molar mass of nitrogen is 14, oxygen is 16. So that's just the ratio of the molar masses. If you've got 2 oxygens, it's 32. 2 times 16 is 32. Okay, so the first one is the molar mass ratio. The second ratio is the ratio of the atoms. So 1 nitrogen atom to 1 oxygen atom, 1 nitrogen atom to 2 oxygen atoms. So the second one is the ratio of the atoms. The next question here says, write balanced chemical reactions to show how nitrogen monoxide and dinitrogen pentoxide are formed. Okay, so we've got the reaction between nitrogen and oxygen. So I'm going to start off there. I'm just trying to move this down slightly. Okay, all right, so we've got nitrogen plus oxygen is going to form nitrogen monoxide. Now, just to balance, we need a 2 in the front there. Okay, so that's the first one. The second one, nitrogen plus oxygen forms dinitrogen pentoxide. Okay, here we need to balance as well. Now, I'm going to do the oxygens first because the oxygens look a little bit more complicated. Well, the nitrogens are balanced at this point, so our oxygens first. Now we've got a 5 and a 2, so we need the lowest common multiple, which is going to be 10. So if we times this oxygen here by 5, we get 10. And if we times this compound here by 2, we get 10. Okay, so 10 oxygens, 10 oxygens. But now we've got 4 oxygens on the right, so we need to put 2 in the front there to get 4 oxygens on the left. And then the last question, which NOx has the most energy stored in its bonds? This X is just the ratio. So in other words, which one of these ratios has the most energy stored in its bonds? That's going to be this last one, the dinitrogen pentoxide. Why? Because each bond has chemical potential energy in it. Okay, you need to add energy to break bonds. So if there are more bonds, it means you need to add more energy. And so the last one is going to have the most stored energy because you actually need to overcome that to break those bonds apart from each other. Okay,